Okay, welcome everybody. My name is Michael Luke. I'm a particle theorist in the physics department here. It is my great pleasure to introduce our colleague, Yanni Khan, who's giving today's colloquium. I'll start out by saying that Yanni has remarkably broad talents. As an undergraduate at Northwestern, he received degrees in both physics and music, the upshot of which is that, in addition to being an accomplished theoretical physicist, he's also one of a very small number of professional Baroque French horn players in North America. So that blend of technical discipline and creativity shows up pretty clearly in his scientific work as well. He received his PhD from MIT in 2015, where he was awarded the APS Sakurai Dissertation Award, and then held postdoctoral positions at Princeton and Chicago before joining the faculty at the University of Illinois at Urbana-Champaign. And in 2024, we were fortunate enough to be able to lure him to Toronto, where he joined the particle theory group and also holds an affiliate position with the Vector Institute. Yanni works at a very interesting intersection. At the one hand, particle theory, and on the other, the theory of machine learning and artificial intelligence. In his particle work, he's well known for influential work on dark matter, proposing new ways to search for it, and thinking deeply about how theory connects to experiment. He's worked on a wide range of ideas for dark matter detection and has played a major role in how the field thinks about connecting theory to real searches. But over the past several years, Yanni's been one of the people leading a growing effort to bring physics-style thinking into machine learning. He uses tools and perspectives from statistical mechanics, field theory, and geometry to ask questions like, what is a neural network actually learning? Why do scaling laws work so well? And what really happens during training? What's especially nice about Yanni's perspective is that it goes both ways. It's not just, let's use AI as a tool for physics, but also let's use physics as a tool for understanding AI. So today he's going to give a talk about this in a colloquium entitled Physics for AI for Physics. So please join me in welcoming Yanni Khan.
Thanks so much. It's a pleasure to be here. I've actually given the colloquium at Toronto before I was a faculty member, but it was in 2022 over Zoom. And I remember just sitting in my basement and talking to a computer screen. And so thank you to the many of you who asked me questions then, whose faces I was not able to see, but hopefully I can see your faces now. And please continue to ask questions. I'd love to have a discussion about the many things that I'm going to bring up in this talk today. Can everybody hear me okay? Fantastic. I tend to talk very loud. I think on my teaching reviews it said, Professor Khan started very loud, but eventually moderated. I'm going to forget that I'm wearing a mic, but hopefully if there's like feedback or anything, just let me know. Okay, so I think it is fair to say that we are in a very interesting time in the history of science and humanity. So when I given this talk before, I had a question mark by this title. I think it is fair to say we can remove the question mark now. This is an example of the kind of thing that AI can do. So Google's Nano Banana image generator says you can type in the following 1, 2, 3, 4, 6 words, create a storyboard for this scene. You input a picture, and conditional on those words and that picture, out comes an extremely hyper-realistic storyboard meant to replicate a hand drawing of something that you can make a movie out of, complete with like the tape on the pages taped to the table. Over here is an example from a paper from OpenAI, actually a physicist at Vanderbilt that was seconded to OpenAI for a period of time, trying to ask, can ChatGPT actually do physics? And the conclusion is, like, with a little bit of prompting, yes, it can basically do exactly the kind of physics that a highly competent graduate student can do. Maybe even more strikingly, this is a plot from a nonprofit that's meant to track the progress of AI. And what it's showing is the year versus the equivalent amount of time it would take a human to do a task. So this is basically like, how is AI doing? So can AI basically half the time correctly accomplish a task that would take a human, a few seconds, minutes, hours, 10 hours? And the conclusion is, like, you have to squint a little bit. There's going to be a lot of log plots that show up in this talk. But there's a doubling time of roughly 7 months. And no one really knows where this trend is going to end. Now you even have agents that can write code, can start to act and plan anonymously, and even last weekend started their own social network. I don't know if anybody saw that appear in the New York Times and various places. So something really interesting is going on. And I think our role as physicists is when we see something interesting in the world, whether it be literally experiments that we do or just some phenomenon, it's our job to understand it. So the hard problem of neural networks is, why is a trained neural network giving the results that it is? So for those of you that have never seen a neural network before, These pictures aren't that helpful, except kind of just as motivation. There's some data that comes in. It gets passed through some series of operations again and again and again. There tends to be this iterative structure. Each iteration is called a layer. So something is repeated L times. Maybe it's some affine transformation with a nonlinear function. Maybe it's some more complicated thing. This is called a transformer. Or as XKCD puts it, this is your machine learning system. Yep, you just pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. That is not an unfair cartoon for what machine learning is actually doing at an operational level, but somehow something that resembles intelligent thinking behavior comes out. That's really fascinating. So this is a hard problem, and I call it the hard problem in analogy to the hard problem of neuroscience, like what is consciousness? Like it's a really hard problem, and so as physicists, when we're confronted with a really hard problem, we try to break it down into subproblems that are easier to solve. Okay, so subproblem number one is what is happening during training? So training is a process by which you start with a set of numbers. Here I've shown you this histogram, which is kind of in blue here. And then you stir the pile of linear algebra, meaning you define some loss function, some measure of how good your network is doing at predicting something you want to predict. If it gets it wrong, you update those numbers a little bit according to some rule. You do that again and again and again, millions or billions of times. And all of a sudden, a neural network that wanted to call this thing a 2, this thing a 3, this thing a 1, calls correctly this image a 9, this image a 2, this image a 1. Okay, so the 0th order thing you could do confronted with a set of numbers is make a histogram, right? So here's the histogram of the numbers after the network has been trained. Okay, it looks different. Something has happened. Can we understand this process more quantitatively and ask, are there any quantities we can measure about these numbers that can give us some predictive information on what the network will do when it's confronted with some data that it hasn't seen before? Okay. Hard subproblem number two, where do these so-called scaling laws come from? Okay, so the prototypical example of a scaling law plot is this one from a paper written by a bunch of either physicists at the time or ex-physicists, now all of whom are ex-physicists because they work at AI labs. That a common theme that you'll see again and again in this talk. So this is the number of training examples you have. So the test loss, the performance of your network is a function of the number of training examples. And it seems to go down on a log-log plot like a pretty good power law. So you might have heard a picture is worth 1,000 words. I kid you not, this log-log plot is worth $1 billion. And in fact, is probably the reason for being of the AI company Anthropic that was founded by a bunch of these guys that wrote this paper. Because if you have a predictive rule for how well your network will do when you add more and more data, you don't have to check every point in the middle. Every point on this plot from this OpenAI blog post is a training run for a larger and larger network that could cost upwards of tens to hundreds of millions or even billions of dollars. But if you know how you're going to do when you add more and more data and more parameters, you don't need to check every point in the middle, and that's what they're showing here. Now, this is log linear, which is why it's a curve, but their eventual performance, so they made GPT-4, was pretty close to what you would have predicted from this power law. Okay, so this is extremely important for modern AI. So those of you that are in my machine learning class, I mentioned this today, like this is already at the forefront of what people are really interested in studying, because any attempt you can make to change this exponent to steepen this power law saves you billions of dollars and also makes your AI systems better and better. But just as a phenomenon, you see straight lines on log-log plots, and a physicist goes, okay, what sets this? What sets this power law? Okay, the third of the hard subproblems is, well, once you have a neural network, can you peek inside it and ask what it learned? So there are various attempts at doing this. The interpretability team at Anthropic has put together these really interesting mind maps. They've found a way of basically extracting features from their networks. And if you kind of look, they categorize them. Okay, this feature fires for references to citations in scientific papers. And they have like some table of like some tens of thousands of these different features, which is interesting, but like, it's hard to get any quantitative understanding out of a picture like this. Other physicists, including my PhD advisor and some of his former students at MIT, made pictures like this. You can peek inside a neural network trained on physics data and make these kind of psychedelic pictures that you can maybe interpret using some tools from physics. But we really don't have a standard way of doing these kinds of interpretability studies. But I would say that if we want to use AI to do science, or make sure that it does what we want in society at large, like it doesn't, go evil and start injecting all kind of malware into our code. It's mandatory to understand something about what is going on the inside. Okay, so what I want to argue is that you can use tools from physics to at least address these subproblems, and I'll go through that in the talk. But then closing the circle for physics for AI for physics, one might ask, in physics, where is our corresponding moment of like technology so advanced that it's indistinguishable from magic, in the words of Arthur C. Clarke? I think we can all agree that ChatGPT and Claude and all these coding agents and LLMs are pretty amazing, and that if you asked yourself from 10 years ago, could you have an AI that could literally write a scientific paper end to end from a 5-word prompt? Most of us would have agreed that that sounded crazy. What's interesting to me is that we've been using neural networks, at least in high energy physics, for like 35 years. So this is, I believe, the first paper proposing using a neural network to classify particles at high energy colliders. Note the date. This is from 1990. And that's a network with 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes compared to the billions that we have today. But if scale is everything, if more and more data is all you need, if we kept every byte of data from the Large Hadron Collider, we would have many, many, many thousands or millions of times worth of the internet of data. And so maybe all we need to do is figure out a better way to use all that data, and then all of a sudden we can make amazing advances in physics. It's certainly true that AI has been useful for physics, but I think it is fair to say that apart from AlphaFold, which one could argue is physics, but at least the Nobel Committee argued was chemistry, that we don't have a corresponding kind of magical leap. We haven't discovered a completely unexpected and new particle using AI thus far. How do we improve this situation? I don't have a good concrete answer, but I'll make some suggestions and open the floor for discussions at the end. Okay, so the rest of this talk, I'll try to motivate for you why studying machine learning and AI from this perspective counts as physics. I'll give you 3 examples, so spherical cows for these hard subproblems where we've tried to make a little bit of progress down each of these roads. And then at the end, ask how we might get to our ChatGPT or AlphaFold moment in physics and really use this transformative advances in AI to make transformative advances in our field. Okay, so to address the elephant in the room, is this physics? Great. So we all agree. In all seriousness, I think what's really amazing about a place like Toronto is that shortly after Jeff Hinton won the Nobel Prize, we invited him to give the Martin Lecture in physics, which means that this is a place that really adopts the attitude that anything can be physics. And no, because I think the ideas. I mean, how many of you were at his Martin Lecture? Just out of curiosity. So, I mean, I think he made some very interesting points that like it's the motivation and ideas from physics that led to the advances that eventually led to things like ImageNet and the deep learning revolution. And I think the way that we think as physicists can be very valuable across a wide variety of disciplines. And I strongly encourage opening those disciplinary boundaries. In fact, I see some computer science people in the audience, which is fantastic. Also, if it's funded by a big foundation, then it counts. And so in some sense, like this new Simons collaboration for physics of learning is a justification that what we're doing counts as some kind of physics. Okay, but in all seriousness, what is physics? Well, if physics is work done by physicists, then basically every paper I'm going to cite in part 2 of this talk was either written by people with PhDs in physics, people with PhDs in physics that were either working in academia or got their PhD and then went to industry. And so from that perspective, we're doing something very, very correct. If all of these advances in AI are being made by people that had PhDs in physics and the way that we traditionally teach physics, then that means that there's something about our approach to very complicated subjects that transfers well across fields, and we should try to exploit that as much as we can. On the other hand, I think we have a lot to learn from our colleagues in other fields, and I think the example of biophysics is an excellent example. Nobody here questions whether biophysics should count as physics, but that was not true 20 years ago. And I think the right thing to do when entering a new field is not declare that you know what all the right problems are and that here are your tools and you're going to come and solve your field for you, but it's to ask people who are working in the field and who have been for a long time, what are the questions we should be interested in, and how can I bring a new perspective or a new set of tools that will help us solve the problems that we're both interested in solving. Okay, now less glib answers. So why might physics be useful? So neural networks have the following properties. There's an enormous number of constituents. So the number of parameters is in the order of billions or trillions at this point. The number of data points is also numbering in the billions or trillions. the initial state, in other words, the parameters that you fill your neural network with before you do anything, you can draw from a known distribution. If you code up your own neural network on your computer, that's usually some Gaussian distribution, but you can make it whatever you want. There's simple microscopic dynamics. The learning rules are very, very simple, but there's emergent behavior at scale. Like, for example, you train a network on some English text, and all of a sudden it can answer questions in Persian. So that was unexpected, but physics is full of emergent behavior, especially in many body physics, right? You pack enough electrons into a material, and all of a sudden they behave as if they're massless, right? Where did that come from? But when we see phenomena like that, we don't throw up our hands and say, oh God, I have no idea what to do. You come up with an effective theoretical description that shows that there's some phase transition, and then you try to describe the system on either side of the phase transition. I think that kind of reasoning can be very useful for neural networks. Another reason physics might be useful is that we're very good at building spherical cows. In other words, when I describe physics to undergraduates, I often say that physics is the science of getting a good enough answer and then telling you how to make it better. Like, we don't want the right answer. We want a good enough answer. We'll make whatever approximations we need to get a number out of a calculation. And then if that's not good enough, we'll revise it. And there's all kinds of spherical cows that one can build depending on one's background in physics. If you're a condensed matter physicist, you might like to think of things in terms of neat field theory or spin glasses or longevity dynamics. If you're a high energy person, you might like perturbation theory. If you're an experimentalist, you might like the fact that you can literally do your own experiments as much as you want on your computer without having to wait for the LHC to turn back on. Really, I mean, as somebody who likes to work close to the theory experiment boundary, I find this an incredibly exhilarating aspect of this field. So especially in this department, especially in the physics department at U of T, where Earth and planetary physics is part of the physics department, we do not just throw up our hands and give up when confronted with a complicated dynamical system. We approach it using the tools of physics. Okay. Once again, I will rely on XKCD for my final couple examples about why physics might be useful. So this says fields arranged by purity. So sociologists, this guy says sociology is just applied psychology, which is just applied biology, which is just applied chemistry, which is just applied physics. Okay, in the cartoon, this guy says it's nice to be on top. I say we should cross that out. Let's not be jerks. And then the mathematician says, oh, hey, I didn't see you guys all the way over there. I think you should actually read this as a log plot, right? So on the right are kind of like formal proofs for worst case scenarios. And famously, there's a paper called the no free lunch theorem for optimization that scared a lot of people off AI because you can prove that when averaged over all possible problems you might try to solve, a neural network will do no better than random guessing, which is true, but vacuous because the problems that neural networks solve are not random problems, they're structured. On the other hand, there are groups, including the interpretability group and Anthropic, that explicitly say they take inspiration from the field of neuroscience, treating a neural network as if it were a found brain in the wild, but instead of being immersed in a vat of soup like it is in your head, you literally know every single number to machine precision, and you can ask it as many questions as you have time and patience to answer with like basically no fMRI noise about trying to poke that brain and ask how it responds. That's great, but it kind of treats every individual neural network as just sort of some instantiation, some sort of creature that you found and you just want to kind of poke at. Whereas physics tries to be a little bit in the middle. So what we sacrifice in rigor, so we come over here, we gain in flexibility. So instead of trying to describe one brain, we try to describe an ensemble of brains and how the average behavior might look. That's kind of the traditional physics approach. Thinking also about the data that is used to study neural networks. Okay, so all the way over here is like natural language. I'm not a linguist, and trying to describe language using numbers, the fact that it works is actually just kind of crazy in the first place. I think in Jeff's talk, he mentioned some intuition for why this might happen. But at least for me, that's too complex. There are too many rules, there are too many edge cases. Grammar developed organically over tens of thousands of years. There are whole fields devoted to this. That's not the kind of data that I know how to study using my toolbox. All the way over here, you have data that's drawn from a Gaussian distribution. Okay, whoever has like studied a Gaussian distribution in any physics context ever? Okay, everyone should raise their hand. Right, that is our spherical cow, and then everything else kind of goes from there. But it's too simple. Like certainly, data in the wild is described by more than just its mean and its covariance. So physics data, I want to argue, I think is just right that it has a low dimensional core kind of dressed by some high dimensional fluff. And my example will come from particle physics, but actually last week's colloquium was an amazing example of a similar kind of system, this time from the context of many-body quantum mechanics. So I think physics is full of examples like this that might be good models for data to try to come from here and still derive formulas and push a little bit closer towards the natural data that we're actually interested in understanding how neural networks are trained on. Okay, so maybe just one more motivational story. So, as a strawman argument, one might say, okay, neural networks are so complex, like how can you ever make progress using these very simple tools? So I want to give you a story that came from my field of particle physics in the 1950s and 1960s. There were so many experiments that when they turned on, they saw pictures like this. Okay, so imagine you didn't know any particle physics and you try to train a neural network on data that look like this and just ask it what particles are there? There's all kinds of stuff going on. This is I believe either a bubble chamber photograph or one of these photographic plates. But the point is that there's all these particles, things are spouting around, things are going all over the place. And in Willis Lamb's 1955 Nobel lecture, he said the following: "I've heard it said the finder of a new elementary particle used to be rewarded with a Nobel Prize, but such a discovery now ought to be punished with a $10,000 fine." So there was so much data, no one knew what to do with it. There were two camps. So there was a camp of people that thought maybe there is an organizing principle. So this fun quote from Murray Gell-Mann: "It's fun to speculate about the way quarks would behave as if they were physical particles instead of purely mathematical entities." Right? So he thought he was building a spherical cow, little did he know. Or maybe it's totally hopeless. There's another camp of people that said, look, there's no framework I understand for these strong interactions. I believe the association of fields with particles to be totally empty. This will never work. The amusing fact is that they were both right, in a sense. So it turns out that actually things get less complicated the higher energy you smash the particles together. That's called asymptotic freedom. And so all they needed to do is build bigger and bigger colliders, and all of a sudden things simplify. This is what the Nobel Prize in 2004 was awarded for the discovery of asymptotic freedom in the strong interactions. However, the other approach led basically directly to string theory, and is useful today in understanding things like conformal field theory, which then feeds back on things like phase transitions and equivalence classes of systems in condensed matter physics. This picture, actually tells you a little bit about the triple point of ice. So I think the story here is that we might not get so lucky with neural networks, but we'll certainly learn something by trying. And so I think at least applying the set of tools might not give the answer, whatever that means, but at least some lessons from our field tell us that when you're confronted with a system that looks like it doesn't have an organizing principle, it might have a bunch depending on which way you slice it. Okay, so let's start with the first of these hard subproblems. So what I'm going to show you is a set of pictures to argue that if you have a neural network and you add more and more and more and more layers, that's better up to a point, and then it starts getting worse. So why is it that when you iterate this structure again and again and again too many times, the performance suffers? Turns out you can actually understand that using these tools from physics. That might not be the most practically useful for modern neural networks right now, but at least the step in a direction of explaining some things that seem like they're very hard to explain if you just treat this as a big black box with an enormous number of parameters. Okay, so the spherical cow here is a network with an infinite number of parameters. And so you might say sending something to infinity seems like it makes it harder, to which I would counter all of thermodynamics and statistical mechanics is in the thermodynamic limit where you send the number of particles to infinity and all of a sudden everything simplifies. So much the same thing happens here. So let's say our goal is to learn some function, so f of x equals y, but I'm going to use an infinite number of parameters, but I'm going to treat that infinity in a very special way. I'm going to send the number of neurons in each layer of this network to infinity while keeping the number of layers finite. So it turns out some work that goes back to work that was started actually here by Radford Neal, and then also continued by some physicists and generalizing to networks with more and more layers, showed that actually you get Gaussian distributions both before and after training. So that's nice. That's why this is our spherical cow, because we know how to analyze this. The distribution of possible outputs of this network, conditioned on the random parameters, infinitely many of them that I start with, is some nice mean zero Gaussian distribution whose covariance is determined by properties of your data. After you stir the pile, you train this thing to try to minimize some loss function. The distribution is still Gaussian, but its mean is shifted away from zero. It's learned something. The mean is determined by this object called the neural tangent kernel, which is roughly speaking like a matrix of derivatives of the output of the network by all of the individual parameters. Okay, so there's kind of two matrices that determine the statistics of your infinite neural network. One of them is K that specifies the variance where you start, and the other one is H that determines where you end up. Okay, so how do such networks train? Well, what's nice is this Gaussian statistics comes from basically the central limit theorem. You're adding up an infinite number of things, and when you do that, variances eventually become small compared to means. So if I were a high energy physicist, I would call this a free field theory. And so at every step of training, the evolution is very, very simple. This object H that governs where I end up actually doesn't evolve during training. It's frozen. And so at every step of training, all I'm doing is a linear transformation of my data. So in some sense, so this tells me this cow is too spherical. I have infinitely many parameters, and all of a sudden what I've recovered is linear regression. Like I tried to do something very, very smart, and what I ended up with something that is quite stupid. Nonetheless, this actually very nicely describes what goes on. And for those of you that are in my machine learning class, you're going to reproduce this plot for one of your final projects. So this is a cartoon from a Wikipedia page that shows that if I train an ensemble of neural networks that are sufficiently wide, sufficiently large number of neurons per layer, that the spread in that ensemble and also their average value on some simple approximation tasks like match a function that passes through these 5 points matches very well this prediction from just taking the spherical cow approximation. So something correct is happening here, but it can't describe everything, in particular because this object that governs what is happening during training doesn't ever learn from the data. It's just frozen at whatever random value it happened to have at the beginning, and it never changes. So the way to perturb that cow away is to say that any real network is not going to have an infinite number of nodes. It's going to have a finite number. And you can use a kind of a physics-inspired perturbation theory to expand in 1 over a large number as your small perturbative parameter. Okay, the equations get ugly. This is kind of a mess. But the point is there's a finite number of things that you can measure in an ensemble of networks. You can take averages and variances and stuff that do, in fact, update this NTK that is the object that governs training of this neural network. So these functions over here that did not appear on the right-hand side before, whose correlation functions are given by these various things shown here. And you can measure them in a network with fixed width and varying depth. And what you see is that eventually when it gets too deep, everything kind of explodes and gets kind of chaotic. So what this is telling us is that this right-hand side, the thing that is telling us how our network can update its representations, can learn from data, increases the deeper I make the network. But if I make it too deep, then things kind of go crazy. So my one entry point to this project was asking, well, can we fix this problem? The answer is yes. Involving an interesting bit of random matrix theory that was actually originally developed to do lattice QCD, which is like nuclear physics and high energy physics. So again, kind of a funny combination of disciplines. It turns out that if you replace your initial distribution of parameters with another distribution, that coming from the distribution of orthogonal matrices, and you measure those same things, they all now flatten out. So again, you don't need to know what any of these objects are, but there's an obvious difference between the shape of the plot on the left and the shape of the plot on the right. For the plot on the right, things are not growing anymore if I make the network have more and more and more layers. And so if you believe the analysis that these objects govern what happens during training, this tells you that past a depth of, I don't know, about 20, nothing much is changing. And so the behavior of the network shouldn't change too much as I make it deeper and deeper. Okay, so we did that experiment. And what you see is that for the standard choice of initial parameters, the kind that you would get if you just coded up a neural network using all the default assumptions, as you make the network deeper and deeper and deeper, not only does the best loss you achieve, so lower is better, that gets worse and worse, it moves up, but also it takes longer and longer and longer for the loss to start decreasing, for the network to start learning anything. Whereas if you use this other initialization scheme, all the curves eventually degenerate onto a single one, meaning that the dynamics eventually becomes independent of the number of layers. The reason I said this is not so useful practically is that you might say, well, look, the best that you did was this small number of layers anyway, where there's basically no difference in the plot on the left and the plot on the right. To which I would say, you're absolutely right. However, the goal of this is to show that you can make some measurements you can use some theory and you can make some prediction or post-diction that is then backed up by other experiments you can do. That entire iteration, unlike doing a high energy or dark matter experiment, doesn't take 3 years in a team of 50 or 1,000 people. It takes like me, my student, and my colleague and friend Dan Roberts, who's now at OpenAI, and like, I don't know, like a year of grad student time and like a couple CPU days. So if you like doing experiments, this is the field for you. Okay, so again, we can say something quantitative and predictive about the behavior of neural networks during training using reasoning inspired by physics, in particular, this branch of random matrix theory and perturbation theory. Okay, so for the second of these hard subproblems, so where do scaling laws come from? So just to remind you, the empirical thing that's seen is that more data, more parameters in your network, more CPU hours all lead to better performance at various rates. Okay, this is the original plot that I showed you. This was first seen in large language models, but it's now seen everywhere, including in physics applications, both in theoretical physics studies, so trying to approximate QFT amplitudes using neural networks, but also in experimental physics. And actually, my student Abraham pointed out this plot to me from the Atlas collaboration at the LHC, trying to train a flavor tagger for models of various sizes. You see very, very similar scaling laws. The reason you should care about this is I exaggerate not at all. This power law is driving an order 1 fraction of the US stock market. So the entire data center boom is predicated on the idea that more equals better in a predictive and quantitative way. So if for no other reason than for the safety of your retirement fund, you should want to know what determines this slope. Okay, so the spherical cow, again, it's going to seem like way too simple to possibly be useful. It's doing linear regression, like the stupidest thing, like fitting a line that goes through some points. But now it's not a line. It's a function, a linear function in a much, much higher dimensional space. Hundreds, thousands, hundreds of thousands of dimensions where all kinds of interesting things can happen. So the first observation that is kind of interesting is that if you have a data set consisting of some vector of numbers, okay, so to train a machine learning model, you need to somehow turn your data into numbers. Maybe your data naturally takes the form of numbers like momenta of particles, or maybe it's words and you need to have some map from words to numbers and then use that to train. But at the end of the day, you have some vector X and the Greek letter alpha or beta will label the element of your data set. From any data set, you can form the following matrix. Take the dot products of those vectors, but the dot products corresponding to different data vectors, right? So this is like a covariance matrix, right? So the variance of an individual element will be like the mod squared of that data vector. Data that are dissimilar are going to be orthogonal. One interesting thing about very high dimensional spaces is that basically any two vectors are approximately orthogonal because you're dotting so many things together that you never get a very, very large number. So that's how maybe thinking about this as a high dimensional problem is different than maybe your intuition from low dimensional examples. But it's seen on natural data, both on text mapped to numbers and also all kinds of image data, that if you take this matrix and diagonalize it, again, a thing that physicists would do when confronted with a matrix, the eigenvalues tend to follow a power law spectrum. Not exactly, like there's some large ones and there's some small ones that fall off. You have a finite data set, but somewhere in the middle, these things all have this very nice linear behavior on a log-log plot. Okay, if you then say, let me assume that my data was drawn from a Gaussian distribution with this covariance matrix and perform linear regression on that data in order to match some target, using tools of random matrix theory, you can show that you get exactly these kinds of scaling laws with both the number of parameters and also the number of data points. Okay, again, why would you think that linear regression is a reasonable model for machine learning at all? Well, that was part of the point of spherical cow number 1, is that at least when neural networks get very, very, very big, they are doing something kind of approximating linear regression. So now we're stacking assumptions on top of assumptions, but we're basically trying to do some curve fitting. We're trying to explain how a power law here in a covariance matrix can give you a power law in the loss, both power laws in the number of data points and also the number of parameters. And these works, again, all by either physicists or ex-physicists, were able to show this in, I think, a pretty convincing way. Okay, now maybe to close the circle for the first time in this talk. So the traditional use of AI in high energy physics was machine learning the following set of data. So if I collide two strongly interacting particles together, that might decay into, the thing that I make might decay into some other particles, but then every one of those particles spits off other particles again, by exactly the same reason that strong interacting physics in the 1950s is so complicated, the strong interactions get stronger and stronger and stronger as my energy goes down or my time increases. So as I go out from the center of my collision, I spray off more and more and more stuff. Eventually, I get this spray of particles all roughly along the direction of my original particle that's called a jet. So what is a jet? It is a list of numbers like that. So this is a simulated one, but it's a list of like 203 vectors. So momenta x, y, and z, or whatever coordinates you want. So the correlations among all of these numbers encode something about what's happening in the middle. And the classic machine learning problem is, how do you distinguish the quote, quote, interesting events, where this one particle decayed into 3 others, from quote, quote, boring events, where I just made a quark or a gluon just by itself, and then it also formed these jets, but it didn't decay into anything interesting. So this is a classic application of machine learning in high energy physics. What's neat is if you think about this from kind of the lens of data geometry, there's something quite interesting and subtle that if you were trying to come up with an interesting, complicated data set, you wouldn't have just done this, but nature seems to have handed it to us. Okay, so it turns out that a fixed number of particles live on a manifold called Lorentz invariant phase space. If you've ever taken quantum field theory, you've seen this manifold before. It's topologically equivalent to a sphere. Okay, so this is it has dimension 3n minus 4. So if I have 4 particles, it has dimension 8. So that's an 8-dimensional sphere. But a particle that has 0 energy might as well not be there. So if your particle is massless, I can literally imagine taking the energy less and less and less and less. One subtle thing about quantum field theory is you can't actually count photons, because a 0 energy photon looks exactly the same as a photon with a tiny amount of energy that your detector didn't have the resolution to measure. Okay? So I can get rid of a particle and get down to a lower dimensional manifold that is still equivalent to the original data that I had. But I can actually go back in the other direction. I can split one particle into 2 that are going in exactly the same direction, but sharing the momenta in some way. There's no way of distinguishing 2 particles that went in exactly the same place in my detector at exactly the same time from one particle. So that's how I get back up from this lower dimensional thing up to the higher dimensional thing. So this fact that how many particles is actually not a well-defined question in perturbative quantum field theory means that the manifold that my data lives on, I think the mathematical term is called a stratification. It's like this nested series of manifolds, starting from my progenitor particle going all the way up to infinity, because I can have arbitrarily many particles that have arbitrary low energy. Thinking about data that lives on this object is really interesting, because you can compute the kind of things you compute in QFT1 or QFT2 live on fixed dimensional phase space. Like here's the probability distribution for a quark to split into 3 other quarks, for example. But nonetheless, there are things that you can compute that don't care about how many particles are in your collection of data, as long as they respect this IRC, infrared and collinear safe property, that they are insensitive to the presence of an additional 0 energy particle or particle that's exactly collinear. So you can kind of use different physics-inspired features and calculational techniques to go back and forth between this collection of nested spheres and some lower dimensional stuff. Okay, the reason this is nice is that I don't know what the probability distribution of images is. Okay, so here are 2 images from Google's image generator. Clearly these are related in image data space, whatever that is, but I don't know of a single knob that I can turn that continuously takes me from seen in the morning to equivalent seen at night. Maybe that thing exists inside the network, and it'd be pretty amazing if it was, but I don't know how to describe that quantitatively. I do know all kinds of knobs that I can turn to calculate things about this distribution of physics data. We know what manifold it lives on if I have a fixed number of particles. There's some natural embeddings, what space this thing lives in, and QFT tells us how to compute distributions on it. And this is what I mean when I say that physics data is like a low-dimensional core dressed by some high-dimensional fluff. The fact that I can have observables that are insensitive to that fluff means that I can kind of identify the core dimension of the data, and then I can start to ask quantitative questions about it that would be much harder to do in the natural data context. So inspired by that, we can start to ask, can I compute these scaling exponents of these scaling laws as seen on this jet data? In our case, let's not worry about literally the real world. Let's just take simulations of that, a thing that physicists are also very good at doing, making simulations of very complicated data. Okay, so we did this. We showed that you see on this kind of standard classification task, you see these scaling laws. There's different scaling exponents depending on the way that you embed the data. There's also power laws in the covariance matrix. And then ongoing work with some folks here and also external collaborators is to try to compute this data covariance spectrum from first principles for different processes, so different knobs that I can turn in my data distribution related to scaling laws, and then try to have some sort of angle on the predictive theory of scaling laws that maybe we could take one step closer to understanding why this is happening in the real world. Okay. So moving on to the third of these hard subproblems, and kind of continuing on this theme of using jets, so high energy physics data, as a model of data. Okay, so again, just to bring home like why natural data is special. So here is a random data of 256 pixels. Okay, there might be more than that here. I can't remember the actual number. If you had 16 by 16 image and every pixel could be black or white, you would have 2 to the 256 possible images. All of them to your human eye would look like total noise, except for the ones that were like all black or all white. Okay, but if I randomly assign a label to every one of those images, the number of image label pairs is doubly exponential. It's 2 to the 256, greater than all the atoms in the universe, whatever your standard of way too large to worry about is. But like, that's not the data that our eyes are good at processing. That is, right? This is from this possible set. It has all kinds of structure. There's like a foreground and background. There's like a person with like a head and leg and arms and stuff. And so the set of real world data occupies a much, much lower dimensional subspace of the set of all possible data. Physics data, as I've argued, has the same kind of structure, not just high energy physics data. Also, last week's colloquium was giving an example from many body physics. And so I think that like physics, all of its branches are full of examples of models of data that we can use to try to extract some quantitative answers for how you can classify this, but not that. So the spherical cow model here is this really neat kind of toy model of hierarchical data. So if you think about grammar, so grammar has these grammatical rules that two words can be next to one another if they satisfy certain properties, or if I have a subject, then it needs like a noun predicate and a verb predicate and that kind of stuff. So you can think of it as living on this kind of tree-like structure, where like I have some concept, and then I have some some grammatical parts of speech, and then I have the instantiation of those things as choices for my vocabulary. You can also think of natural images again as like this leopard is like a head, and then its paws, and then on its head there are some ears, and every one of these things kind of segments all the way down. So a model of data like that is you basically fix some tree structure, you fix some number of vocabulary elements, so like all the different colors you can fill in these nodes with, and then you have some rules that say like blue always goes to orange, green, or red, red. And you have, say, V colors at every level, S splitting, so your S is 2, every one thing always splits into 2, and then M rules per symbol. And each input sequence, basically all the way at the end, that's the data that you actually see, is associated to a unique tree where every single node is determined, as long as the number of rules is sufficiently small compared to the number of possible vocabulary elements. Turns out this is basically equivalent to what's called a Potts model in many body physics. So there actually is a very concrete physics analogy, but like this is just some toy model of data that exhibits a hierarchical structure where there's exponentially many possible input sequences, but the allowed sequences are a much lower dimensional subset. Okay, if you train a particular kind of neural network on this data set, you see a phase transition, by which I mean quite literally a phase transition with a diverging power law something, which is a susceptibility that I'll define in a second. So the thing that you train is called the diffusion model, which in one sentence is a neural network that is trained to remove the noise from noisy data. So you take data, you add noise, and you train a neural network to remove that noise. Okay? So if you do that, so here's a picture of a wolf. If you train this diffusion model, but you don't add noise all the way such that the image is totally random, you add just a little bit of noise, then you ask it remove that noise. It doesn't give you back the exact image you started with, but note what happened. The eyes changed color, but kind of not much else. So if you imagine this picture of a wolf as like these high-level features, which is like wolf, and then you have head, eyes, and eye color. So you're changing things down at the bottom of the tree, but it's not propagating all the way up to the top. You see exactly the same thing in this toy model of data, where because it's a toy model, you can solve all the equations analytically. If you add a critical amount of noise, eventually you get so confused that you can never reconstruct your original sample, and like this wolf would turn into a banana. Okay? In this tree, you see that because you see correlations. Basically, the reds are things that change between the original sample and the noise and then denoise sample. Those correlations propagate all the way up the tree to give you an error in your node up here, which you can think of as the label of your data set. For images, is it a wolf, a dog, a banana, or whatever? And you literally, as a function of the diffusion time or the amount of noise you add, you see a peak in the susceptibility defined as basically the spatial correlation function of these errors in these nodes. So spatial correlated changes propagate to give you a peak in the susceptibility, but only for data that has this kind of tree-like structure. So this is basically a diagnostic of, does your data like to live on this kind of low-dimensional set that has this very nice structure? And with all that, I can now just show you a picture, but this is another way of looking at a jet. So what is a jet? It's one particle that spits off two other particles that spits off some more particles. And so thinking of this data set as like another toy model of hierarchical data, but one which has some more interesting bells and whistles. There's a continuous label at each level, the momentum of the particle in addition to what kind of particle is it. I have this equivalence class where if I have zero energy, it might as well not be there, so I can make particles disappear. I have a strong coupling constant that is increasing throughout my tree, and at some point it becomes so large that I have to switch over to another model entirely, where all these quarks and gluons confine into the particles that I eventually see. That's some process that we model via other toy models in simulated data that adds another level of complexity. But at the end of the day, I have this lowest level whose correlations must be encoding something that's happening up here. So we hope that basically running the same set of tricks on this toy model of data with these extra knobs that we can turn. What particle did I start with? What's the value of the strong coupling constant up here? Do I turn on or off charge conservation? I can understand something about what's happening with the same equivalent correlations in real data. So the very first steps that we've done in order to make this work are, if you know something about your data and you are so sure that it is true about your data, you should make your neural network respect that and not force it to learn it approximately. So the fact that we know so much about physics, all these things about IRC safety and whatever, all come from the fact that my theory respected energy and momentum conservation and the symmetries of special relativity. So if I want to make that true everywhere, I have to basically construct one of these neural networks that forces the data to live on my data manifold at every step in the process. If you don't do that, you always find that the events that you generate have a tail that violates energy conservation. And so it's very hard to know, are the correlations you found real or are they spurious due to this unphysical thing that we know shouldn't be there? Thinking of this as a manifold, there's actually some really beautiful work on doing diffusion models on manifolds. For those of you that do earth science, the earth is a sphere, and so probably this kind of approach is actually very, very useful. It's beautiful in principle for our case, but it ends up failing in practice for annoying numerical reasons. So instead, we use basically an ancient physics trick, which is that we map our data to an auxiliary space so there are no constraints, but with a non-trivial distribution, such that when I do the map back, which is basically a Lorentz transformation and an energy rescaling, I recover the distribution that I want. And actually, this was the algorithm that has been used to sample random particles that is used to generate our fake data since the 1980s. And just to show you some pretty movies, so I start with some distribution where in this plane, which is a projection of my 5-dimensional data, it's kind of concentrated here. Eventually, you'll kind of see this thing like kind of spread out. So the distribution that I want that's quote, quote, pure noise for me is just totally uniform in this triangle. And then if I sample from that triangle and I run this process backwards, eventually you'll see this thing kind of converging towards the center and recovering the original distribution that I started with. So this is like the -1th order step to doing these kinds of interpretability studies, but at least it lets us, use our physics knowledge to be able to do machine learning on a data set where we know things really well, and we want to use that knowledge in order to understand things better. So there's a whole bunch of questions we want to answer along this direction that we were fortunate enough to be funded by CFAR through this project called the Alignment Project, trying to understand how can we make AI do the things that we want it to, and understanding how the inner workings are going on is I think, a necessary step to doing that. So there's lots of projects here that I think I've talked to several of you about, but happy to discuss more. So maybe in just the last minute, let me go back to AI for physics. So I think the lessons from industry, and by industry, I really mean like our colleagues from physics who've now gone into industry, is high quality data with hierarchical structure is key. So AlphaFold leveraged the fact that there's this enormous data bank of protein structures that they were able to train a model on in order to accurately solve the problem of protein folding. Given a sequence, predict the geometric structure in real space. Okay, we have lots of high quality data with hierarchical structure from the LHC, from condensed matter experiments, from what have you. Scaling the data, the model size, and the compute predictably improves performance. This is a lesson that I think is just beginning to be adopted in high energy physics. The very first scaling law plots on real experimental data, not even published. This is like an Atlas internal publication note, meaning it's sort of maybe not quite ready for prime time, but hopefully it will be soon. We see the exact same phenomenon on real high energy physics data. So more data, more compute, you do better. The other really surprising thing is that correlations are everything. And I think the best illustration is I literally typed the following 5 words into ChatGPT. I typed a cat riding a horse, and it generated me this image, right? So meaning that like the probability of a cat riding a horse conditional on the whole internet, right? Sampling from that distribution, this is a sample from that distribution. And in some sense, like, so in retrospect, why can we believe this would work? Well, if I say a cat riding a horse, I don't need to say I want a picture. It's pretty clear from context I'm talking about a picture because like that's what a caption of an image on the internet would look like. So associated with images would be captions that say like a cat riding a horse. You know, given the fact that like the pictures of horses on the internet always look a certain way, like, you know, cats are, you know, tend to be kind of this like cartoonish thing, then maybe that's why the facial expression is the way it is. All of these correlations are just there in the data and they're very hard to enumerate, but you throw enough compute at it and the model will just figure it out. So this, I think, is like all of physics. Like there's no mystery in the strong interactions that is not encoded in the correlations of all the particles that we can see in our detector. There's nothing hidden. So I think if we use this phenomenology, we can learn an enormous amount of stuff about physics. And so my personal take is that like machine learning is best at understanding data that we have, like the standard model, not data that we wish we were there, which I think is like anomaly detection, unless we can simulate it at scale. So here are a couple examples of things that you can imagine doing, you know, really, really large simulations for, including last week's colloquium. This is not an exhaustive list. I think all areas of physics can contribute with this philosophy in mind. And so just to conclude, because I know that I'm about 2 minutes over. So physics for AI, I think we have the right tools and philosophy to solve interesting problems in a field that really is in its pre-scientific era where experiment is way ahead of theory. We have tools that work. We don't know why they work. That's where I think the ideas in philosophy of physics can be helpful, at least in part. And then for AI for physics, like our data is a gold mine, like quite literally. We have centuries of practice taking, manipulating, storing, simulating high quality data. And scaling lets us tap that research to do scientific discovery. This is a virtuous cycle, and we should all keep doing it for as long as all these things are possible. So I'll just thank my collaborators, and I'll stop there. Oops.
Thank you for a great talk. Can take questions now.
Yeah.
So let's talk about coding bias into your model. Given of a manifold or some underlying sensitive physics. How are you going to discover something?
Good. So the question is about enforcing bias. Like if I put in the thing that I think is true, I can never get out something that's different from that. So I will say that the kind of biases that I want to put in are the ones that are backed up by literally centuries of evidence. Like every experiment that we've ever done has confirmed that energy is conserved, momentum is conserved, and special relativity is a good symmetry of the world. I would say that you have to have extremely strong priors on that being true, and you should condition any evidence to the contrary on those very strong priors. There are other priors that we should probably relax, but I think those are pretty robust.
Oh, sorry, question online? Oh, okay. Question online. Okay. Will the deck be available after the presentation? I'm a layperson. I'll need another go at the slides.
I'm not sure what I will do my best to post this on my website. No promises, but I'll make an effort to do that.
Oh, okay.
Thank you. Thanks for the talk. So in machine learning, there's a long history of studying the adaptivity of algorithms to structure in the data. So the most classical example that we teach students in intra-machine learning is the nearest neighbors algorithm naturally adapts to data that is living on a lower dimensional manifold in some higher dimensional ambient space. And crucially, the algorithm adapts to that without knowledge of the dimensionality of that manifold, and its learning rates behave as if it had known that without you specifying it in the algorithm. And there are other instances of this. So kernel methods adapt to the smoothness of the function they're approximating without you specifying the smoothness constant and so on. So I guess the question is, or I wonder if your jets, you could study learning algorithms that adapt to the structure of the jets naturally without having been told that structure. It might even be that large language models can do that. And there might be some sort of, that might be one way of thinking about how that structure benefits learning.
No, I'm glad you brought that up. And I wish I had the plot in backup, but we actually did see a scaling law in k nearest neighbors trained on jets with a different scaling exponent than all the other ones. But the trick is that you have to define the distance metric carefully. The distance metric is not Euclidean because you have this thing about like zero energy particles don't matter. And so if I add that vector, then splitting two things into two collinear splitting something into two collinear particles. So basically it's a variation of the Earth mover's distance. But I don't know enough about the analytical tools to study k nearest neighbors, but we should talk because then ideally, so basically we see 5 different scaling laws for 5 different ways of preprocessing the data. If we can understand all of them based on properties of the data alone, then I would say game over, we're done. So any theoretical tools that we have for identifying any of these things, I'm totally game for using. Yeah.
I guess, do you think there are good applications with like physics-informed neural networks to do simulations of physics maybe more efficiently than?
Yes. In fact, that was basically what these pictures were showing, right? So emulators of high dimensional simulations, right? So in other words, a simulation is way too, the real world is way too fine-grained. Kind of butterfly effect aside, I don't need to know the temperature, down to the millimeter scale in order to predict the weather tomorrow. So if we can figure out what a good coarse graining is and let the machine learning do the interpolation, that would be amazing. And I think, weather data is an example, cosmology data is another example. And so I think this is actually a very powerful use of AI in physics, as long as we have enough training data to be able to benefit from the scale. Yeah.
Just on topic of interpretability, when we model physical problems with AI, how are we meant to cope without a precise representation of that model, given that we don't fully understand how AI models train or in their final output, why they make the correlations that they do?
So I think there's 2 approaches to that problem. So number 1 is you can try to peek inside the network at every step during training and ask what is it doing and what is it learning? The other kind of approach, which I think is this exemplifies, is in this case, I don't really care what is going on in the guts of the model, because I can use the fact that a model is able to approximate a property of my distribution in order to learn something about my data distribution. So I think these two tools actually go hand in hand. They're very complementary. But the physics example here is, okay, so I didn't say this in detail, but okay, so this is a 5-dimensional distribution. I'm showing a 2D plot because on top of every point in this plot is 3 Euler angles. So the fact that this diffusion model was able to learn this 5-dimensional distribution, these 2 axes are actually Lorentz invariant numbers. And so if it found the correct distribution for the Lorentz invariant variables and also isotropy in the angles, it's learned the whole thing. In some sense, I don't care in this context how or why it learned that, but I know that if it can do that, then I've correctly learned the Lorentz invariance of the system. And it's probably due to the fact that I'm using Lorentz transformations to do this mapping in this auxiliary space. So I think you have to go back and forth. We're not going to be able to do all of it all at once, but you can kind of do interpretability either mechanistically, looking at the parameters of the model, or after the model is trained, you can sample it, you can use it, and you can relate that back to things you know about your data and ask sort of what has it learned.
So in your second example, you're almost treating networks as a first-class object in computation.
I don't know that terminology, but I'll say yes because it sounds right.
So maybe time for one more question.
Hello. So towards the end, if I understood you correctly, you said you seemed not very optimistic about anomaly detection. However, towards the start, you're talking about the mass amounts of data produced, say, in the LHC,
Yeah.
and how basically we need better triggers to maybe find some new physics. So if anomaly detection is maybe not very optimistic, then what would you think we can do?
Yeah. So like the strong dynamics of QCD. And I'm like, personally, I'm very embarrassed that it took me this long to come around to this. This is basically the phase transition that my PhD advisor underwent. He was a supersymmetry theorist and decided that like jets were all there was during my PhD. I never worked on jets. And now like almost 10 years later, I guess more than 10 years later, like, oh yeah, that was right. I mean, I would have loved to have found new physics at the LHC or found dark matter. The fact that we haven't is disappointing, but like we should not treat the petabytes of data that we have as garbage. Right? It's gold. Like there's still things you don't understand about QCD. Literally every collision at the LHC is QCD. Like something about this process should now be interpretable at scale. So that I think is, so, you know, like the very kind of nuts and bolts thing is, can you use a diffusion model trained on simulated jets to improve your hydrogenization models in simulated data? Like, and there's a number of collaborations that are explicitly focused on that. You know, and there's other applications too. Yeah.
Thank you.
Okay. Oh, it's one more question and then we'll online question. Okay. 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 Dick Bond says, you emphasized AI and high energy experiments, but the universe seems to be fundamentally hierarchical and we expand the universe in prominences, usually through using a spherical cow correlations. We do dipoles and quadrupoles, but the cosmic web has bent filaments joining clusters, i.e. complex multi-scale correlations. We do train using observations and limited simulation ensembles. The question is, do you see that cosmology and amplitudology can help to understand what happens with AI?
So, I mean, again, I think like this idea of using physics data as toy data sets, I think is an excellent example. And I think like cosmology data is another example of that. And I think the question is, you know, what is like the minimal you know, what's the analog to like simulated jets with non-perturbative physics turned off in cosmology? You know, the problem is that like, you know, if gravity were that simple, we wouldn't need n-body simulations. Like these filamentary structures, as far as I understand, they don't tend to appear from analytic calculations. They just drop out of the complicated n-body dynamics of gravity. But if there are a way to get an analytical handle on that and be able to compute something about your data from the other side, then you can kind of, you know, close the AI for physics for AI circle. And so I think, yeah, I mean, obviously cosmology is another area where all these tools make a lot of sense.
Okay, well, we've, I think, run out of time. So let's thank Yoni once again for a great talk to the talk.
Thanks.